Well, how did you do it writing down this vector? All we need to do is look at, as you go from the tail to the tip, how far in the x and y direction do you go? And so the answer is either of C or D. Both of those notations are fine. I'll tend to use the I hat, J hat notation. The most common error I see students make at this point in their learning is to look instead at where the tip of the vector is relative to the origin, and so that would have them come up with A. But that isn't correct. Remember, that's not what we mean by writing down a vector. One way of thinking of it is that the meaning of a vector is that it is the location of the tip relative to the tail of the vector. So here's an assortment of vectors, A, B, C, each written in component form, and you should pause the video and verify that you see how I got those. But I want to clarify some notation and terminology. For example, we say that A is the sum of its component vectors, A vector x and A vector y. And you can see, just looking at it, that A vector x is just 4I hat. But what we mean when we say ax is not the component vector, but the component, the thing that multiplies the I hat, which in this case is 4 meters in all of these cases. And so, for example, B, I could say that the component vectors are bx vector, which is I hat, and by vector, which is -6j hat, and both of those are in meters. But I could also say that just the components of B are what I would call bx with no vector symbol, which is just 1 meter, and by, again, no vector symbol, which is -6 meters. The real advantage of component form is that it makes vector addition really easy. Here's an A, here's a B. I've drawn the vector addition, and you just have to collect the i's and the j's. Or in other words, you add the x components up, so you're going to get -6 meters plus -2 meters, I plus 3 meters minus 5 meters, j, and so that's it. -8 meters I minus 2 meters j. Multiplying a vector by a scalar algebraically is even easier than adding. You just multiply both components by the scalar. So for example, if we start with this vector A, and we multiply it by 3, we're just going to multiply the x component by 3 to get 6, and the y component by 3 to get 9. And as we expect from our graphical intuition about this process, we get a vector that points in the same direction as the original one and is 3 times as long. We're often going to be working in one dimension during this course. That's because it really makes very little difference to the physics whether we're in 1D or higher dimensions, and so I will tend to introduce each idea in one dimension and then generalize it to 2D later. Now, it's easy to get away with ignoring vectors when you're working in one dimension, but I'm going to say you shouldn't try to get away with it, and I'm not going to. I am going to stick to good vector notation even when I'm working in one dimension. I want to show you why. So I'm going to set up a situation here. As you'll see in the next unit, a displacement is the difference between a final position and an initial position. If that doesn't mean much to you yet, don't worry. I'll introduce it in Unit 2. For now, all I'm doing is setting up a situation where I have to subtract one vector from another. So suppose that the initial position is 2I hat meters, and the final position is 5I hat meters. So here they are, where note I perhaps should have drawn them right on top of each other, but that would be hard to read, and so I've offset them from each other slightly. To subtract them, let's take RF, and we'll flip RI around and put it tail to tip with RF, And then delta r, the displacement, is here. Working with the numbers, I have delta r as just this, and that gives 3 I hat meters. Well, so what? Well, notice something. The magnitude of RF was 5 meters, and the magnitude of RI was 2 meters. And so it looks like I could have just subtracted their magnitudes to get the correct magnitude, 3 meters, of delta r. Can I always do this? Well, to answer that, I'm going to keep working by example. I'm going to take the initial position vector and I'm going to change it around to negative 1 meter I hat. So now the vector subtraction looks like this, and delta r is here. So in numbers, that's like this. Notice it's no longer true that the magnitude of delta r, which is 6 meters, is the magnitude of RF, which is 5 meters, minus the magnitude of r, which is 1 meter. Notice a magnitude is always positive. That's no longer true. So apparently this doesn't always work, and so we shouldn't use it. We only use rules if they always work. What is true, though, is that the x component of delta r is the subtraction of the x components of RF and RI. And that's just what we've already seen as how we do vector addition and subtraction. So, even though we're in one dimension, we should still pay attention to the difference between magnitudes of vectors and their components. In particular, notice, vectors are neither negative nor positive. They have direction, and that's different from being negative or positive. Magnitudes, though, are always positive by definition, whereas components of vectors can be positive or negative. Keeping this straight will save you a lot of confusion later on. So, for example, these 3 statements all have very different meaning. I encourage you, and this may be on a homework assignment, to draw some arbitrary vectors a and b and work out what each of these statements would mean in pictures.